This is the executive team.
I'm Shiraz.
I'm Delaney.
I'm Jackson.
I'm Priya.
I'm Shannon.
And together, we make Cool Beans Inc.
The kidney is the most common organ donated, and in Canada, $1.9 billion or $90,000 per person per year goes to dialysis treatment compared to $65,000 for kidney transplant. This highlights the importance of ensuring the success of these donations for cost savings and quality of life improvements. To reduce the chance of kidney failure following surgery, the time the kidney is warm without a blood supply, called warm ischemia time, should be minimized. A warm ischemia time greater than 60 minutes is associated with a 23% increase in risk of death or kidney failure. When a surgeon places the kidney inside a patient, the kidney warms until the surgeon finishes attaching the vascular system. This takes on average 45 minutes but can take up to 80 minutes. Current solutions to mitigate warm ischemia time utilize large bags of ice, aluminum tubing, or damp paper towels. These solutions are incompatible with better surgical methods that are less invasive and reduce room for a cooling device. Cool Beans Inc. is innovating upon current methods to solve this problem. The objectives of this project are to minimize the warm ischemia time a kidney experiences during surgery, design a compact device that is compatible with current surgical techniques and meets regulatory standards. The focus of this project is only on the initial part of the surgery. The retrieval, initial cooling, and transport of the organ is outside of the scope of this project.
We set the following constraints for our design to ensure its safety and success. Correct size and fit. The device must be able to accommodate a large range in kidney sizes while maintaining a tight fit. Cause no harm. The design cannot predispose any risk towards the organ or cause adverse effects. Sterile. There can be very serious harm to the patient if the product is not sterile. Meet medical device standards. This product must meet the regulated standards for medical devices, as approval is necessary for implementation in hospitals. The following criteria were developed to optimize our final design: minimize warm ischemia time, minimize interference with surgeon, maximize ease of use, minimize cost, minimize environmental impact, and minimize training time.
After determining the details of the problem, brainstorming sessions took place and each solution was evaluated based on several factors such as functionality, cost, and ease of use. Constructive feedback received on our deliverables were taken into consideration when finalizing the details of our project, such as the materials used and sustainability of our product. We created a rapid prototype of our design to allow individuals to easily visualize the concept, and we are committed as a team to continually improve our design to facilitate its launch to market. We used a Gantt chart to stay on track with tasks and deliverables, and modified it accordingly with the timeline changes that occurred for this presentation, as well as the final design report. Decision matrices and Microsoft Excel were used throughout the product development phase to justify having certain features and to optimize parameters for having minimal heat transfer to the kidney.
The first design idea is a continuous, closed-loop circulating coolant through tubes. This alternative was not chosen due to its dependence of external elements of a pump and refrigerant system. The second alternative is a thermoelectric cooling pelcher plate. With the nature of the design being comprised solely of electrical components, it will be tremendously difficult to be completely waterproof and biocompatible without increase in complexity or cost. The ultimate design solution was found: a tight-fitted, moldable jacket-inspired design with multiple layers of insulation. And now I'm going to break down each component. The first being a disposable 2-layer polyethylene insulation sheet with a geometry of a 2D kidney surface area. This includes the first layer of 0.9% saline solution that is in direct contact with the kidney, and it's followed by a pressurized air insulation layer that is split up into longitudinal parallel sections, similar to the concept of bubble wrap, but with rectangles rather than circles, and this is to reduce the heat transfer from the body to the kidney. The second component is a flexible, smooth, filleted, disposable 316L stainless steel spine on the external portion of the insulation layers, and it's designed to be interchangeable with varying organ sizes. I just wanted to note here that we did assume that the hospital will have a refrigerating system in which the insulation layers can be stored and maintained at the correct temperature. Now here we see how this puzzle piece structure effectively folds. The features of the solution include simplistic adaptation to current market products, resulting in the ease of use and low initial cost. It's energy efficient as it's not dependent on electricity. It's a portable and mobile solution without the restriction to external devices that need to maintain the heat transfer. It maximizes surface area, contact with the kidney, and it's a closed-loop system with no risk of leaks or solution contaminants to the body. Here is a rapid prototype demonstration and integration of effective folds used to maximize the surface area coverage. And this meets the criteria, as you can see here, as there's no interference with the surgeon, as it's a tight fit around the kidney. In this video, it's modeled as a sweet potato. It also avoids contact with the critical blood vessels. Here in the video again, it's modeled as a red and blue toothpick structure. And as you can see, it's extremely easy and quick to put on, as it's anticipated to take under 30 seconds to do so.
In order to perform the calculations necessary to measure the heat transfer through this device, the following assumptions were made. The shape of the kidney was approximated to a cylinder. The shape of the device is approximated to a hollow cylinder, one directional transient heat transfer, the outer surface of the device is touching 37-degree body mass, the thickness of the pressurized air layer is set to 4 millimeters, and the holes in the polyethylene bag and stainless steel spine are negligible.
For our design, we needed to calculate the amount of saline solution that can absorb the heat from the body and the kidney without changing the temperature of the solution for 45 minutes. This is called the latent heat of condensation and helps us determine the optimal thickness of the saline solution layer, denoted with an X in the image.
The latent heat absorbed by the saline solution ice layer was calculated using the energy of phase changes equation. An additional assumption was made that the density of the ice would be equal to the density of water, and phase change, HFG, would be calculated as the enthalpy difference. The calculation was performed using a 45-minute surgery duration. Therefore, the latent heat absorbed by the saline solution ice varies by the radius of the saline solution insulation. The heat transfer from the kidney to the saline ice solution layer was calculated using thermal resistance through a cylinder, the assumed shape of the kidney. The average temperature was calculated over the range of 4 degrees Celsius to 0 degrees Celsius. Therefore, the heat transfer from the kidney to the saline solution layer is 7.69 watts. The heat transfer from the body to the saline ice solution layer was calculated using multi-layer thermal resistance through a cylinder. The total thermal resistance was calculated assuming the insulation layers were in series. Therefore, using the body core temperature and total resistance through the insulation layers, the heat transfer from the body to the saline ice solution is 37 degrees Celsius over the total resistance. Using Microsoft Excel, several values of the saline solution layer were plotted to determine the correct thickness, X, to satisfy the above equation. Therefore, the thickness of the saline solution layer should be 4.6 millimeters, rounded up to 5 millimeters, in order to maintain the temperature of the kidney during the first 45 minutes of surgery.
After the ice layer melts, the kidney temperature will begin rising, and to model that rise, the system is simplified to a cylinder with one-dimensional heat flow with a convection coefficient determined by the heat flux through the device at the initial temperature difference. This graph shows the kidney's core temperature over time after the ice melts. This model predicts that the temperature after 90 minutes of surgery is 10.2 degrees Celsius.
In order to confirm that having the pressurized air layer in our design is effective, calculations were performed for a kidney jacket without a pressurized air layer in order to compare between the two. With the pressurized air layer removed, as seen in the diagram shown, the time required for the saline solution to change its state from ice to liquid without a temperature change is 123 seconds. With the pressurized air layer, it took 45 minutes, or 2,700 seconds, for this to occur. Therefore, having the air layer in our design is very effective in insulating the kidney for a longer duration during the surgery.
As for safety, codes and regulations were abided by, but more specifically in the design, all elements were biocompatible. Specifically, a 316L stainless steel spine was considered as it contains less nickel to limit allergies. All components are disposable, and this directly correlates to decreased contamination.
This device impacts society by increasing patients' lives and quality of life. The increased confidence from the public in the success of kidney transplants will also correlate to more people registering as organ donors, expanding the donation pool and decreasing the transplant wait times. The emissions from the production of this device were calculated, resulting in 1.38 kilograms of carbon dioxide, 0.00672 kilograms of methane, and 4.8 times 10 to the negative 12 kilograms of cyanide emissions. As this design is not reusable, the use of 100 devices produces 350 kilograms of waste. All of the biohazardous waste can be sanitized, melted down, and reused, reducing the negative environmental impact.
The economic costing of the design was based off of the unit price for each material along with the reusability. Taking into account the unit price for 3 polyethylene bags, 0.9% medical grade saline solution, and 316L stainless steel, the cost per unit is $3.78. And since none of the materials for the design are reusable, the cost per 100 units is $378. However, it is noted that although parts of the design are not reusable, the polyethylene and stainless steel are recyclable, improving economic and environmental impacts of the design. The cradle-to-grave process representing the life cycle of the design is broken down into a flow diagram on the right, highlighting the importance of proper disposal and recycling of the product.
Some potential risks that may be encountered by using the product are patient allergies to polyethylene, for example, localized freezing of the kidney surface, and fragments of the device being left in the body by the surgeon. Some uncertainties that may affect the use of the product are the duration of the surgery and the kidney size and shape. The calculations performed are also based on assumptions that may not accurately represent the functionality of the product. With patient safety as our highest priority, Cool Beans Inc. will be working towards minimizing these risks and ensuring the product is tested extensively prior to market release.
In conclusion, we've developed a device that can improve the success rate of kidney transplants. Device parameters were determined by heat transfer and thermodynamic modeling. Economic and environmental analysis was done to determine costs and impacts of the device. The next steps we have planned are to build a prototype, get approval from Health Canada, and contact manufacturers. Thank you for watching.